Hi, everybody. This is group 12 for assignment 1, and we did topic 1, which was rock, paper, scissors strategy, where we record a ton of different rock, paper, scissors games with different players who are each designed with a specific strategy. And then we take stats over how they played out against each other after many games. My name is John Ryan. I'll be speaking first, and then I'll be followed by my partner, Paula Mazzone. I did the Python portion. So we decided that we would develop in parallel. We felt that'd be much more, considering the scale of the project, much more efficient than if we had to wait for each other to do specific implementations and whatnot. It worked great for us because we were both able to finish our implementations within a day. Really great. We decided we would do different languages because we were developing in parallel, obviously. And I decided I would do mine in Python, and my partner Paulo did his in Rust, which is great because they're completely unique implementations, and we'll get very different runtime statistics due to one of the languages, Python, being interpreted and Rust being compiled. And then we chose to log our progress through GitHub. You can see the links here on the right. Obviously, I did mine in Python, and Paulo did his in Rust. So our goals, we wanted to, based off the topic 1 outline, is we wanted to have thousands of matches play out. Obviously, we end up simulating way more than that. And we want to record and display statistics on it. And we want it to be somewhat performant. So we both had the goal of achieving O of N time, which we were able to achieve. For my Python implementation specifically, Paula will talk about his. It's able to simulate 10 million matches in under 21 seconds. Obviously, Python's an interpreted language, so it doesn't perform as fast as the Rust implementation, which Paula will talk about later. We record every match, and it records move-specific wins and losses, as you can see on the output for mine on the right here. It says specific move losses, draws wins, counts of each move, and overall win-loss ratio. As you can see in this specific shot, Carlisle has an awful win rate. I'll get into that later, but that's largely because it just so happens that of the 5 strategies I programmed into mine, one of them hard counters another person's. I'll get into that later. And it tracks the simulation runtime, as you can see at the final statement there. This was a simulation of, I think, 1 million, which took 2 seconds. So as you'd expect, because it's O of N time, 10 million took about 20 seconds. So why did I develop in Python? First of all, it's an interpreted language, which complements well against Rust when it comes to the runtimes. I'm quite familiar with it. I had programmed in a little bit of time over the summer, so I felt like, just going in with my comfort language, which happens to contrast very well against Rust, would be great for me, be super productive, and I obviously enjoy the clear syntax. Here I show the player class, and as you can see, all that I really do when I create the players, I give them a name and strategy, and then it just so happens that I create a bunch of counters for them, and I track their wins and losses, as well as their history of moves, which, as you'll see later, when I put the players against each other, they do take the opponent as a parameter. So they are actually aware of the opponent's move history, and they do make decisions based off that. So as you can see here, I have players in the bottom left. The 5 strategies that I ended up doing were random, just purely random. One that's weighted towards rock, one that cycles rock, paper, scissors over and over, one that counters the last move of their opponent, and one that copies the last move of their opponent. So about performance, the program runs in O of N time, and this was simulated with a Core i5 12600K. 1,000 matches takes about 2.5 milliseconds, and you can see the simulate function here, and this is how I actually got the time. So pretty much everything in the program is creating classes or saying how the logic will work. Simulate is the only thing that's actually doing any heavy lifting really during the runtime. So all of the time is inside of simulate. And you can see that when it first starts running, it takes time. And then once it ends, it also takes time and then prints out the end time minus the start time to give you the overall time. So for the entire range of whatever I set it to simulate to, it just takes a random sample out of players, which is the list I showed on the last slide of the 5 players, and then it does the choose move function, which happens to take player 2, and then obviously for player 2, which takes player 1. So it is aware of the opponent's moves, and then it gets the winner. Now I update a bunch of counters like, okay, if this person won, give them plus more win, and say it was this move that won and all that. I didn't. That's a lot of lines that I felt like wouldn't fit on the slide very well, so I just didn't show that part. So strategy breakdowns. This is each of the strategies of each of the players. And I wanted to note that the way I chose to do this in Python is with strings. Strings to represent the moves, and each of them obviously has an index inside of moves, which is a list. So that's how the program does a bunch of the logic. So I'll talk about each of these strategies. So you can see when it chooses the move, it checks if there's an opponent. By default, it's set to none. Some of the strategies, like the last 2, do actually care about if they have an opponent. The first 3 don't. So first of all, we have the random one. So this is just purely random. It just does a choice in moves and chooses a random string index. Cycle, though, does rock, paper, scissors over and over again. So it checks if it has history, first of all. And if there's no history, it plays rock, as you'd expect if it goes rock, paper, scissors. And then it determines what's next in cycle. So purely what it does is it takes the index of its last move, and then it adds 1. And then it does modulus 3, just so that we don't, go past the things in the actual list. And this will just make it go rock, paper, scissors, rock, paper, scissors. Next, we have the rock enjoyer. So this one just takes a random integer from 0 to 9. And then if the integer, if it's below 6, it'll just choose rock. So it's a 60% weight. And then if it's under 8, it'll do scissors. And then otherwise, it'll do paper. Then we have counter last. So this one checks, obviously, if the strategy is counter last, and then also if they have an opponent. If the opponent history exists, it'll take that and check what it is and then play a counter move to that move. And then obviously if they don't have history, it just chooses random. So that's like for the first round, but that does not matter if you're simulating. It'll have 0 effect on the statistics percentage wise once you do tons and tons of different simulations. And finally we have copycat, which just checks the last move of the player and then copies it. So it just plays that move.
Welcome to the Rust portion of the rock, paper, scissors strategy assignment. A quick apology for my mic. You might hear some random noise. I don't have a great noise filter on, but I'll do my best to try and keep background noise to a minimum. All right, so just as a brief intro, some of you may or may not be familiar with Rust, but I chose to do my portion of the rock, paper, scissors implementation in Rust. And so let me quickly justify or give you background on Rust before I justify it, why we chose Rust for this portion. And the big pluses to Rust is cargo, memory safety, automatic memory management, strong standard living compiled. Obviously, these are pretty hand wavy, but to go a little bit more in detail, cargo is the package manager and build system, where in C you would have something like CMake. Cargo is just a lot simpler. It's one command to add a new package from anywhere online, or the Rust repo, I should say more specifically. It's one command to run it, one command to run tests. It's just very simple to use. Memory safety, this is probably what's talked about the most in pop media, is Rust is memory safe, and that's true. It is more secure to write on low-level code in Rust where it's available. Of course, there's some caveats to that, but it's pretty universally true. Automatic memory management comes from the fact that it manages lifetimes, and it's borrow by default instead of copy by default. And this has several implications, which makes it, once you understand how it works, it's really quite simple. But before you're at that point, there is a bit to it. Strong standard library. There's nothing here that demonstrates it super well, but there's a lot of support for pretty much everything in the standard library, from multi-threading to SIMD in a portable manner. And it's compiled, so you get fast speeds. Why did I choose it? And this is a lot simpler. I want to stay sharp in it. I've used it quite a bit, but I don't have a whole lot of reasons to be using it day to day at the moment. So this was a good excuse for me to keep my skills sharp on it. And honestly, it's really nice to work in. As you can see, we've got like match statements, and so it's just really easy to work with, even though it is, performance comparable to C or C++. So the brief goals and reality I was aiming for. My goals are have 1,000 matches play out, record statistics, be fast, and display the statistics. And how that actually played out, we've got up to 10 million matches in under 3 seconds. I didn't show it here, but I'll show it soon enough. Record each win-loss match. So I record the results, like what moves won and lost for each match. Record the number of wins, losses, and draws. Forgot an S there, but that's okay. For all the total matches. And show the win-loss ratio and stats. You can see that briefly here for 2 of the 5 strategies that we've got the number of win, losses, and draws, the number of moves that won and lost. And obviously, this is an absurd number of matches, so the numbers are huge. And also, you can see the win losses 1.0 for a completely random. And yeah, that makes a lot of sense. Performance, it should be ON because of the strategies I chose to go with. Sorry. And the strategies, briefly, I did not write them here, but I can go over them very quickly. We've got one person who's totally random, one person that is heavily weighted to scissors. We've got one person that chooses the move that their opponent most often loses with, another person that chooses the most recent winning move of their opponent, and somebody that just goes rock, paper, scissors ad nauseum. So it should be ON. I know I said that one of the move sets was checking the player's past history, but it only checks the last 100, so it's bound to be 100. So theoretically, it's not ON under 100, but as we go to infinity, it's a ON. And we can see that if we graph out the run times compared to the match count, that this is very clearly a straight line. 1,000 matches takes 167 microseconds, just lightning quick. Really quickly, I'll go through the timing and tech stack I was working with. So I was using an i7-10700F at 2.9 gigahertz with 32 gigs of RAM on Ubuntu 24.04 on WSL on Windows 10. I find WSL is much nicer to work with stuff like Rust than the native Windows versions. I'm using the Rust extension for VS Code, and I'm also using the VS Code Remote Connect to WSL and Cargo 1.89. As for the timing portion, this is the exact code snippet, but obviously I cut out the for loop so you could more easily see what's going on. But the surrounding code is the same. So we have start time. I just record the time at the start of the loop. I record the time at the end of the loop and take the between time as microseconds. And then when it's printed to the screen, obviously nobody really wants to see microseconds. So I divide it by 1,000 to get milliseconds, or you can divide it by 1,000,000 to get seconds, but milliseconds is usually better for anything under, I don't know, a few million iterations. And yeah, you can see more detail about all my specs up here on the WSL output. And where could we go to over engineer this? Now, I was just looking up speed and I got a couple images. They're not related, just thought they might be funny. So the ways we could easily over engineer this and just take it to the extreme would be the low-hanging fruit of multi-threading it. This would bring some problems with synchronizing some of the strategies, but there are some simple workarounds. Even if I just have to mutex it, it'll probably still be faster as we get to the millions and billions. Better organized structs for cache. I made no intention to optimize for cache coherency or cache lanes. So stuff like this may or may not be optimal in memory. I don't know. I didn't look into it. But if I really wanted to push the performance, I would have to do that. And a faster RNG algorithm. I haven't profiled it, but usually RNG algorithms are a tiny bit slower than they need to be. And this matters as we get up into the insane numbers. Obviously, we got up to 10 million in this example here, but a billion is still too long. And thank you. That's it for my portion.
All right, so here's a sample of 1 million matches. So each player played around 400,000 games. You'll notice that our purely random player has a perfectly even ratio. You end up with a pretty great win-loss. Notice that Rock Enjoyer, person who's weighted 60% towards Rock, 20% to the other moves, has a pretty bad win-loss ratio, and Cycle ends up with a really high ratio. Now, it just so happens that they counter Copycat perfectly. Now, this is purely because rock, paper, scissors, that order specifically, happens to play a move that beats the last move every single time. Rock always loses to paper, which always loses to scissor, which always loses to rock, and it cycles that forever. So in the case that the opponent is copying their last move, they will always beat them. 100% win-loss ratio. And against counter last, because they are countering the last move, they will actually end up with the exact same move as Cycle. So Cycle goes rock, paper, scissors. Charles, who does the copy last, sees that they played rock last turn and therefore plays paper because that beats it. Oh, what do you know? They both played paper. They draw 100% of the time. So specifically because of the strategies I chose to play, Cycle draws 100% against Counterlast and wins 100% against Copycat with this specific cycle order. Now, if I change the cycle order to be the exact inverse, instead of playing the move that always beats the last move, it'll be playing the move that always loses to the last move. So we should expect that instead of drawing 100%, this should be very different. And instead of losing 100%, this should be very different. Again, 1 million. Okay, so you'll see, yeah. So now Cycle has a even win-loss ratio, and Counterlast is losing because if you counter their last move, you'll actually get beaten. So Cycle goes from scissors to paper. Counterlast sees they played scissors. What beats scissors? Rock. Oh, what do you know? They played rock into paper. They lose 100% of the time now against Cycle. But Copycat, on the other hand, always wins because Cycle's playing the move that loses to their last move. So you go from scissors to paper. Copycat sees you played scissors last time. You're going to play scissors. Oh, what do you know? You played paper now. So you lost. So yeah, just something I want to talk about for anyone that cares. Kind of cool. If you change the cycle, it has massive effects on these specific strategies and whatnot. Big thank you for watching this presentation video, and I hope you learned something new.